Hello, let's talk about why manual balancing valves do not fit into our modern systems where we use electronic circulation pumps. In Europe Union from 2013 we have only electronic circulation pumps controlled either with constant delta P or with variable delta P. But still, somehow, we still use manual balancing valves, and in a few minutes I will prove why it is wrong and why you are having problems with under balancing, with flow shortage, if you're using manual balancing valves with modern circulation pumps. Actually, in Europe Union, you are not allowed to use any other circulation pumps. So why you are still using manual balancing valves? This is a big question for me. So what I have here, I already prepared the example of a system. Here we have heat exchanger, circulation pump, manual balancing valve, first riser and radiator on top. And here of course we have some more radiators, but this one is the last on this riser, so this one is the most important. And here we have the last riser in my system, and the last balancing valve, and the last radiator with thermostatic radiator valve. So let's calculate how much pressure we need, for circulation pumps to circulate the flow in this my system. Here in the middle, of course, I have also risers, but I will explain it later. Usually for heat exchanger, we are calculating something like 20 kilopascals for heat exchanger. For supply line, let's calculate for supply and return. Let's predict here we have something like 20 kilopascals. For riser, let's say we have pressure losses, also 10 kilopascals. For TRV, let's say we also have 10 kilopascals. For manual balancing valve, this is the last riser, so we usually take something like from 2 kilopascals. It depends from country to country, but for easy calculation, let's say here we have 5 kilopascals pressure loss. Okay? So my circulation pump then will be 20 plus 20 plus 10 plus 10 and plus 5. So in total it will be 65 kilopascals if I calculated right. So let's mark here. We have our pump head here, 65 kilopascals. This is how much I need. And here is my flow, running system 100%. Here is my working point. Okay. What else I need to do? I need to balance my system. I need to calculate how much I need to squeeze this balancing valve to have right flows. Let's say riser here is same 10 kilopascals. I can mark here 10 kilopascals also. For TRV here, let's say also same 10 kilopascals. So I need to calculate now. I need to minus from this circuit from 65 kilopascals. I need to minus 20 kilopascals. Let's say distance here is nearly to 0 kilopascals, so not going so deep. 10, 20, 10 and 10, so 40 minus 65 will be something like 25 kilopascals to squeeze this balancing valve and to have flow everywhere I need. Okay, let's calculate it if I balanced it correctly. It should be also 65 kilopascals, so 20 plus 25 will be 45, 55, 65. So this means this circuit is 65 and this circuit is also 65. So my system now is commissioned and I have right flows where I need. My system is working at 100%, and everything is balanced, commissioned, and runs smoothly. But not always, and let's see how system will work on a partial load. Let's say on one side of building, sun starts shining, and we don't need heating in this part of the building. So let's say here we have some 50% of rises, and those rises just closes, thermostatic radiator valves closes those rises, and now I have not 100% flow, but all I need is 50%. So let's say I need half. My system is at half partial load, and let's see how it is working at partial load. At partial load, here I had 100% flow. So let's assume I have 50% less flow because 50% of rises just close immediately. According formula, if my flow going down with half, with 50%, then pressure losses in a system usually goes down 4 times less. It's nearly 4 times. I'm not going into very detail, but you can check. And let's say this heat exchanger now is working at 50% flow. So this pressure losses now goes down with, I need to divide by 4. So new setup, new delta P here will be not 20, but dividing by 4, it will be 5 kilopascals. Okay, let's say this riser is on the north side and it is working. It needs 100 capacity. It stays same. I am passing on my supply line. So on a supply line, I'm missing 50% of rises. 50% of rises are closed. So this means my 20 becomes also 5 kilopascals. Okay, and let's predict this riser is also working. All neighbors are at home, and this side of building is also on a north side, and they still need heating. Okay, so let's see where our circulation pump is now working, how much pressure we need here. Delta P, I mean, so 5 kilopascals plus 5 plus 5 plus 5 and plus 10 and plus 10. So new working point will be, how much it will be? 10, 20, 25, 30, it will be 35. So somewhere probably here, 35 kilopascal. Okay, so my new, something like this. So system working at variable speed drive, and now circulation pump spins slower and produces 35 kilopascals. 35 kilopascals is enough for the riser, which is the last one. But how it is with riser, which is the first one? Let's calculate how much delta P we need here. So 5 kilopascals plus 25 will be 30, plus 10 will be 40, plus 10 will be 50. So we need 50 kilopascals to have right flow for first riser. What we get is only 35. So this means in a system with modern circulation pump, where we have delta P variable setup, this type of circulation pump regulation is very efficient. It most efficient at these days. So having this setup at partial load, then half of rises closes, I will have shortage of flow into first rises. So this is what happens in systems with manual balancing valves. So this means I am limited if I am, for example, at these days, I'm building commercial building, multifamily building with manual balancing valves. This means I am limited to have delta P constant regulation. So this means my pump is programmed from the beginning to have, let's say, more energy use, of course, more CO2, and I will simply be spending more money just because I am limited. I used manual balancing valves in a system where I should use automatic ones. So there are another videos where I talk about differences between delta P controllers, pressure independent control valves, manual balancing valves, the video with demo stand, and you can find the link in the description. So please take a look and see how manual and how automatic balancing valves work. And my recommendation would be not to use manual balancing valves for balancing. Okay, here we should use delta P controllers, pressure controllers for rises, or there are for smaller systems there are small dynamic valves, RADV. It is called RADV. Dynamic radiator valves, where we can put here dynamic radiator valve, which is pressure independent, and it needs no balancing valves, but it is limited to 60 kilopascals so it can be used for smaller system, or with delta P controllers also it can be used for bigger systems, or we need to use here delta P controllers for rises, and then we can use RANs. Okay, so this is my answer why manual balancing valves are not suitable for balancing in modern systems with modern circulation pumps controlled with frequency converters. And then probably you are asking yourself, so why still manual balancing valves are used? Why still they are being produced? So manual balancing valves, of course, can be used in another, let's say, applications. We can put manual balancing valve here to measure the total flow. We can use manual balancing valves somewhere in mixing shunts, also for flow measuring, for flow verification, if you need that. So manual balancing valves will still be produced, but probably not for balancing, not for commissioning, but just for flow measurement, flow verification. Okay, thanks for watching. If you have some questions, please comment and I will try to answer them. Thank you.